Hello everyone, welcome to module 4. So in this module we're going to discuss kinetics, chemical kinetics, especially focusing on rates and mechanisms of chemical reactions. So let's start with the kinetics. So in this particular module we're going to focus on the reaction rate, how to express the reaction rate, the rate law and its components. Finally we'll discuss integrated rate laws, concentration changes over time. And in the second lecture, we're going to discuss the theories of chemical kinetics, reaction mechanisms, and finally end with the catalysis. So let's start with a reaction. So what's the difference here between a faster reaction and a slower reaction? So think about it here this way. A faster reaction is where all of the reactant is being converted into product in a short amount of time. A slower reaction is where this is still happening, where the reactant is becoming a product, but it takes more time. So chemical kinetics does not deal with the reactant or the product. It deals rather with the time in which the reactant is being converted into product. So let's start with different versions of this wide ranges of reactions. For example, a bomb is an example of a fast rate of reaction. Vegetables undergo a slower degradation. For example, humans also undergo various levels of decomposition throughout their life with increase in age. And you also have trees that stay longer than usual. Their reaction rates are much lower. So what are the factors that influence reaction rates? So first is that the particles must collide in order to react. Second, the higher the concentration of the reactants, the greater the reaction rate. So which means that the higher concentration of reactant particles allows a greater number of collisions. Next, the physical state of the reactants also influences the reaction rate. For example, the substance must mix in order for particles to collide. And third, final, the higher the temperature, the greater the reaction rate. So the reason mainly is because at higher temperatures, particles have more energy, therefore they collide more often and more effectively. So the effect of surface area, for example, a hot nail that glows feebly when placed in oxygen, but the same mass of steel wool bursts into flame. The main reason is because here the surface area is less, but when you put in steel wool, it's a little higher. So sufficient collisions. So notice that here, when this reaction occurs, here the ozone must collide with the nitrogen monoxide for it to form oxygen and nitrogen dioxide. Now when this reaction occurs, they have to have collisions between ozone and nitrogen monoxide, but there can be collisions between ozone and oxygen, ozone and nitrogen dioxide. So this cannot work. So a reaction can only occur if the collision energy is high enough. Now no reaction can occur if the collision energy is too low. So it needs to be a certain amount for the reaction to occur properly. Next, how do you express the reaction rate? So reaction rate is generally measured in terms of the changes in concentration of the reactants or products per unit time. So for example, if you take a simple reaction A to B, so we measure the concentration of A at T1 and we measure the concentration at T2. So the rate of reaction is basically the rate of change of concentration over time. So change in concentration of the reactant by change in concentration of time. So at the concentration of A2 minus concentration of A1 by T2 minus T1. So which can be represented as delta of concentration of change in concentration of the reactant by change in time. So this can be written as the rate. So rate only considers the reactant but not the product. So whenever you see the square brackets, it basically indicates the concentration in moles per liter, and we use the negative sign mainly. So rate here is represented as a negative. So the negative here represents that it is because the concentration of A generally decreases with time. So the rate value will generally become a positive value. So for the rate to become positive, for the product for the reactant we generally put a negative. Let's take a simple example. So three type of reaction rates of O2, O3 and C2H4. So C2H4 is ethylene and ozone react and form ethylene oxide and oxygen. So there are three versions of this reaction that can happen. One is a linear relationship. where you get a straight line relationship. The second is a curved relationship. And finally, third, you have a relationship that goes this way. So let's take a look at each of these and understand how the reaction rate generally works. So let's take the reaction here. So C2H4 plus O3 gives C2H4O plus O2. Now, what is happening here is that you have two main parts here. If you consider the other side as well, so if you consider the two main parts here, so one is C2H4 and the other is oxygen. So notice that as C2H4 decreases, the amount of oxygen starts to increase. So O2 increases with the same rate as that of the C2H4 decreasing. So which means that the rate is nearly the same. So the rate of reaction can be written as, so delta minus delta of C2H4 by delta T is equal to minus delta of O3 by delta T. That equals, now the amount of decrease here is also equal to the amount of increase here, so which means this can become delta of C2H4O by delta T is equal to delta of O2 by delta T. So notice that the amount of decrease here equals the amount of increase here. So the rate at which the reactant is decreasing is equal to the rate at which the product is increasing. Now the same thing happens with H2 plus I2 is equal to 2HI. Gives 2HI. How would you write the rate of reaction here? So now that the rate at which it decreases here is going to be the same, so minus delta H2 by delta T is equal to again minus delta I2 by delta T. Now notice that there are each individual one of them. Now there is a decrease in one here, so which means that originally for each one molecule there is a two molecule production here. So which means that for every molecule this consumes, this produces two molecules. So in terms of the rate of reaction, so which means that the rate at which this is produced is half the time. So it takes half the time to produce two molecules here for one molecule, because notice that for one molecule there's two molecules being produced here. So which means in terms of the amount of time, for the amount of time that it takes to reduce one molecule results in half the time for the production of increase of the HI molecule. So notice that here, because one produces two, so which basically means that for each amount of time in which it reduces one amount, here it increases by two amounts, which means that the same amount of time, it takes only half the amount of time for the production of one molecule. Because notice that rate represents the production of one molecule. Here it's producing one molecule, so we can two molecules, so we can write half of the original molecule. Now, so how do we generalize this reaction? So if you write a reaction as AA plus BB gives CC plus DD, notice that small a, b, c, d are all coefficients. So the rate of reaction here can be written as minus 1 by A by delta T is equal to minus 1 by B delta B by delta T equals 1 by C delta C by delta T equals 1 by D times delta D by delta T. So this is the rate, and this is the general rate formula for a reaction. AA plus BB equals C times C gives CC plus DD. So this is the general rate of reaction. So use the same principle now and try to write down the coefficient of the rate reaction for this reaction here. So let's start with, you have 2H2 plus O2 giving you 2H2. So how would you write the rate here? So it can be minus 1 by 2 into delta H2 by delta T equals 1 by 1 minus 1 by 1 of delta of O2 by delta T. This is the product side, so we can write plus 1 by 2 of delta of H2O by delta T. So this is the rate here. Now what is given in the question? So they have first asked us to explain the rate in terms of this, so we have done that. Second, they have given us that the reduction in O2 is 0.23 moles. So what they have given here is minus delta of O2 by delta T is given as 0.23 mole per second. Notice that they've already given that it is being reduced. So this value can be written as minus 0.23. They are asking us at what rate is H2O increasing. So they're asking us to find delta H2O by delta T. So only use the reaction that between these two here. So the one that is known and one that is unknown. So from this we can write that minus delta of O2 by delta T equals 1 by 2 times delta of H2O by delta T. So we only need this part. So push this 1 by 2 on this side. So it becomes minus 2 times delta of O2 by delta T equals delta of H2O by delta T. Now, so we know this value here, so which is going to be minus 0.23. So we can write delta of H2O by delta T can be written as minus 2 times minus 0.23. So which gives you 0.46 mole per second. So if the oxygen is decreasing by 0.23 mole per second, the water is being increased at 0.46 mole per second. So this is how we can write the rate of reaction for the increase in water. So use the same principle now. Pause the video right here and try to solve these problems. Next, let's get into the rate law. So for any general reaction occurring at a fixed temperature, for example, let's consider the reaction AA plus BB gives CC plus DD. So the rate of a reaction is given as K times concentration of A to the power m and concentration of B to the power n. Now K here is called as the rate constant, and obviously A and B here represent the reaction, the concentration of the reactants, and the exponents here m and n are called reaction orders, and these are generally determined by experiment. Now these m and n values do not have anything, they are not necessarily related in any way to the coefficients A and B. These general reactions are generally determined, these values are generally determined by experiments, and these values will be given in the problems when needed. So now let's find out this reaction orders and what do these reaction orders mean. So a reaction will always have an individual order with respect to or in each reactant. Now for a simple reaction where we are converting a reactant into products, now if the rate is doubled, then automatically the concentration of A will be doubled. So this is an example of a rate that depends on to the power A to the power 1, and this is called as the first order reactant. So which means that if the rate gets doubled at the same rate as the concentration gets doubled, so this is by 2, this is also by 2, then we call that a first order reaction. Now if the concentration increases by 2 but the rate increases by 4, so notice that this is a square relationship, this is a power 1 relationship. So because there is a square relationship, we call this a second order reaction. Now if the reactant increases by 2 but this does not change, stays the same by 1, which means that here it does not depend on the reactant, so we call this a zero order reaction. So third order is much more rare, so we only use first, second and zero order in this particular module. So if the rate does not change when you increase the concentration of the reactant, so this is an example of a zero order reaction. So what is happening here? If rate increases the same as that of the concentration of the reactant, then we call that first order. If the rate if the rate quadruples when A is doubled, so we call that a second order reaction. And if there is no change in the rate of reaction when you change the concentration of the reactant, we call, if the rate does not change when the concentration changes, we call that a zero order reaction. So these are graphs that show in terms of when you plot the concentration with time. So these are graphs that show the relationship between zero, first and second order reactions. So notice that the time it takes generally varies with the type of reaction that we have, right? And the amount of concentration decrease also plays a main role. So in zero order reactions, the concentration is completely utilized in a short amount of time. In first order reactions, it takes a little longer. In second order reactions, it takes much more time for it to completely utilize the reactant. Now, we generally do not use directly the concentration versus time graphs. We more commonly use the rate versus concentration graphs. Now, if the rate does not change with the concentration, we generally get a parallel line. So this parallel line represents a zero order reaction. And in a rate concentration graph, if you get a linear line, a straight line, we call this a first order reaction. And if you get a curved line, we call this a second order reaction. So if you get a straight line, zero order. If you get a linear line, we got it first order. And if you get a curved line, we call it second order. So this here is when you have rate on the y-axis and the concentration of the reactant on the x-axis. Next, let's discuss individual and overall reaction orders. So for example, let's consider the reaction 2NO2 plus 2H2 gives N2 plus 2H2. Now, when you determine experimentally the rate law, this is the rate law. So the rate here represents here. So the K times NO2, so K times NO square times H2. Notice that here the rate law does not have anything to do with these coefficients. So these coefficients and the rate, the exponents do not have anything to do with each other. So this is the experimental rate law. Now notice that NO2 has a second order while hydrogen has a first order. So what would be the total overall reaction order? So the overall reaction order is generally determined by adding up the powers. So when you add up both the powers, we get a 3. So this represents that the overall order of the reaction is 3, while the individual order for NO is 2 and H2 is 1. So which means that the rate at which NO2 doubles, for example, if the concentration of NO is doubled, the rate gets quadrupled. If the reaction of H2 is doubled, then the rate gets doubled. But what if both are done at the same time? So where we double both NO2 and H2, then the rate gets tripled. So what is happening here? So it becomes power 3. So power 3 represents that it becomes 8 times. So this is the term that we are talking about in terms of the overall reaction order. So use the same principle now. Pause the video right here and try to determine the individual order and the overall order of these reactions. Notice that the rate law is already given. So you just use the rate law and directly find your answer. So pause the video right here and try to solve this problem. So use the same principle again. Pause the video right here and try to solve the problem. So notice in this problem, what is also given other than the original problem here is that they've also asked you what are the reaction order in each reactant and overall order, but they've also asked you that what factor does the rate of I minus and BRO minus are tripled and H plus is doubled. So this is the reaction rate. So let me solve that part. So the rate here is K times I minus times BRO3 minus and H plus taken square. Now notice that they are saying that if I minus and BRO3 minus are tripled. So what you can do here is directly write 3 times. So this is triple times 3 times H plus is being doubled. So times 2. So 3 times 3 times 2 square. So this becomes 3 times 4. You have 9 times 4. So that becomes 36. So the rate of reaction changes by 36 times. So when you triple I minus and BRO3 minus and double H plus, so we can consider that the rate increases by 36 times. So this is how we can determine when there is a question that says that one is being tripled or the other is being doubled. So use the factor directly without k, but make sure that the powers are being kept. So notice that the powers are still used. So we don't use the k here, but we still use the powers here. So with this, we can determine the rate of reaction. Next, let's talk about how to determine the reaction orders. So for any given reaction, well, let's consider a plus 2b gives c plus d. The rate law is of the form ka to the power m, b to the power n. So to determine these values of m and n, we generally run a series of experiments in which one reactant concentration changes while the other is kept constant, and we measure the effect on the initial rate on each case. So what we'll do here is that, let's say we have a, b here. First, we generally double this, and we change this, and we keep this constant, and we determine the rate. We keep a constant and then change this, and then determine the rate. Basing on the changes here, we generally use the rates that rate of these reactions, and then use the algebra to determine the actual powers. So let's take an example and try to do that. So these are the initial rates of an experiment. So let's say between A and B. So where we are mixing A and B. Now notice that in the first experiment, so what is done here? We are keeping first, so the initial rate is already given. So we are keeping A, we are changing A while keeping B constant. So this is being kept constant, and we are increasing this. And in the second experiment, we are keeping B constant, and we are changing A again. So using these principles now, so what can we determine by using this principle now here? So let's take an example here of the first two reactions. So in the first two reactions, we are keeping B constant while we change A. So we are using the first and second experiment. So let's consider the problem as rate 2 by rate 1 equals k a to the power m b to the power n by k a to the power m b to the power n. So remember that because the reaction is the same, the rate constant will not change. So we keep k the same, and this becomes a1 b1 a2 b2. Now we already given us the concentrations and the rates, so we also have the concentration and the rates. So write down the rate here. So this is 3.50 times 10 to the power minus 3 by 1.75 times 10 to the power minus 3 equals a1 to the power m. So a1 here is, a2 b2 a1 b1. I'm really sorry for that. So a2 here is gonna be 5.00 times 10 to the power negative 2 to the power m times b2 here is going to be 3.00 times 10 to the power negative 2 to the power n divided by, again, a1 here is 2.50 times 10 to the power negative 2 to the power m by 3.00 times 10 to the power negative 2 to the power n. So this parts get cancelled. Now, so this ones, this is 2. So 2 equals, so power m constant, so we can divide both of them. So 5.00 times 10 to the power negative 2 by 2.50 times 10 to the power negative 2 whole square, whole to the power m. So ones, twos, so 2 equals 2 power m. So it can be written as 2 power 1. So from this we can determine that m equal to 1. So now we know the value of m. Now we have to determine n. So what we have to do in the next case, notice that in the first case that we took, we kept B constant and we changed A. In the next experiment, we have to keep A constant while we change B. So in this, we can consider the experiments 1 and 3. So in 1 and 3, notice that there is a constant change. There is no, A is being kept constant while B changes. So again, so what can we write it as? Rate 3 by rate 1 is equal to k times a3 to the power m b3 to the power n divided by K times A1 to the power m, B1 to the power n. From this we have rate 3, which is 3.50 times 10 to the power negative 3 by 1 is 1.75 times 10 to the power negative 3 equals, so K here is the same, so we can keep that constant. So let's consider A3 here. So A3 is 2.50 times 10 to the power negative 2 to the power m by 2.50 times 10 to the power negative 2 to the power m, and B3 here is 6.00 times 10 to the power negative 3 negative 2 to the power n, and 3.00 times 10 to the power negative 2 to the power n. So these two are constant, so we can cancel them out. So this one's 2's, so 2 equals, so the power is the same, so we can write 6.00 times 10 to the power negative 2 by 3.00 times 10 to the power negative 2 to the power n. So 1's, 2's, so 2 equals 2 power m, so n becomes 1. So we have determined that m is 1 and n is 1. So the rate law here can be written as K times a to the power 1 and b to the power 1. So this is the rate law for this problem. So for this experimental problem here, so this is the rate law here. So this is the rate law. This is how we can determine the rate law for different problems. So use the same principle now. Pause the video right here and try to solve this problem. Remember again, first we keep b constant and find m. So when you keep b constant, we find m here. So here b here is NO2. So first keep NO constant, and from this you can get m. Next keep O2 constant. From that you can get m. So for that, first in this experiment, we're gonna choose 1 and 2 first here for 1 and 2, and for the second experiment, for the second part, we can choose where we're going to keep O2 constant. So O2 constant is 3 and 1, so we're going to use 1 and 3 here. So to determine m, so use the same principle now. Pause the video right here and try to find the values for m and n using this table. So pause the video right here and try to solve this problem. So use these two problems as practice and try to do this at your own pace. So pause the video right here and try to solve these problems. So next, let's talk about the units of rate constants for several reaction orders. So remember that the rate constant does not have the same unit in different reaction orders. So if it's a 0 reaction order, the unit of K is moles per liter second. If it is 1, it is 1 over second or second inverse. If it is 2, it is liter mole per second, liter per mole second. And if it is 3, it is liter square mole per mole square second. Now let's take into consideration of the unit of K. The general formula is liter per mole to the power order minus 1 by the unit of time. So let's take an information sequence of how to determine the kinetic parameters of a reaction. First, we use the series of plots of concentration and time. So you're using the determinant of the slope of the tangent at t0 for each plot. We determine the initial rates, and we compare the initial rates of A that changes when B is held constant. And finally, using that, we find the reaction orders. Finally, we substitute the initial rates, orders, and the concentrations into the rate law and solve for the value of K and compare it with the actual rate law. So these are examples of the integrated rate law that include rate as time as a variable. So for a first order reaction, we know that the rate is minus delta A by delta T, so which is going to be K times A to the power 1. Now, the equation in terms of time is given as ln of initial concentration by the concentration at the time t equals Kt. Now for the second order, it's Ka square, so which can be written as 1 by concentration of A at the time t by minus 1 by the concentration of the initial concentration time is equal to Kt. And finally, for zero order reaction, it is going to be concentration at the time t minus concentration at the time A, initial concentration, equals minus Kt. So these are the three equations that we're going to use to determine the concentration at the time t. So let's take an example. So what is given here? So at 1000 degrees centigrade, cyclobutane decomposes in a first order reaction with a very high rate constant of 87 per second to 2 molecules of ethylene. So they have given us that the initial concentration of cyclobutane is 2 molar. What is the concentration after 0.10 second, and what fraction of C4H8 has decomposed in this time? So let's take an example here. So first notice that it's given that C2H8 decomposes and forms 2C2H4. So which means that here in this reaction, so the rate of the reaction is given as minus delta of C2H8 by delta T. But notice that they've given us that this is a first order reaction. So we know that the rate is K times A to the power. So A here is only one of them, so which is C4H8 to the power 1. Now we know that the rate law basically states that from the integrated rate law we can write that ln of the first order reaction is going to be ln of A0 AT by A0. So it's A0 by AT. So A0 here is C4H8 initially by C4H8 at the time t is given as KT. Now in the problem time is given as 0.010 second. So use that particular principle here. So ln, the initial concentration is given as 2 molar divided by, so we have to find this C4H8 at the time t, is equal to K here is given as 87 per second times time is 0.010 second, so which is going to be 0.87. So this is the amount of the total concentration that has been decomposed. Now we have to find this value here. So when you put ln, notice that ln is equal to log base E. So when ln goes to that side, so it becomes e to the power. So 2 divided by C4H8 at the time t is given as e to the power 0.87. So this value for e to the power 0.87 can be found as 2.4. Now we have to find this value. So C4H8 at the time t can be written as 2 over 2.4. So when you calculate that, that gives you a value of 0.83 mole per liter. So this is at t equals 0.010 second. The concentration of C4H8 is going to be 0.83 m. So this is the concentration. So second, what is in the question next? What fraction of C4H8 has decomposed in this time? So in this time period, how much is the total decomposition? So fraction decomposed is the initial concentration minus the concentration at the time t divided by the initial concentration. So which is going to be 2.00 minus 0.83 divided by 2.00. So which value will become 0.58 or 58%. So this is the amount of substance that has already been decomposed in the time t. So at 0.010 second, so 58% of C4H8 has been decomposed. So this is how you can solve the problems using the rate law. So use the same principle now. Pause the video right here and try to solve this problem. So next, let's get into the topic of reaction half-life. So what is half-life? So half-life of a reaction is the time taken for the concentration of the reactant to drop to half its value. So the amount of time it takes for initial concentration to become half of the initial concentration This time is called as the half-time or half-life. So for a first order reaction, the half-life does not depend on the starting concentration, and it's given by the formula T half equal to ln2 by K or 0.693 by K. Remember that here K is a constant, so which means that T half is also going to be a constant. So because K is a constant. Now, one of the common processes that uses this principle is the radioactive decay. It is also a first order process. So the half-life of a radioactive nucleus is a useful indicator of its stability. So what does half-life basically mean? So let's take a simple example. Let's consider that I had 1 gram of substance, and it takes 2 years for, so let's say for example, it takes 2 minutes for it to decompose into half its time. So 1 gram can become 0.5 grams in 2 minutes. For 0.5 grams, remember that half of this, so half. Now half of this, which is going to be 0.25 grams, take another 2 minutes. Half of this, which is going to be 0.125 gram, is going to take another 2 minutes. Half of this, which is going to be 0.0675 grams, is going to take another 2 minutes. Again, half of this, which is going to be 0.03275 grams, which is going to take another 2 minutes. This way, remember that the molecule will never go to zero, but it rather decreases to a minuscule amount with time. But this amount is a process which we generally call exponential decay. So materials generally undergo exponential decay, so which means that with time it decreases, but it never becomes zero. So for every half, it takes a half-life period. So let's take an example here. So what is given here? So substance A decomposes to two other substances, B and C, in a first-order gaseous reaction. So the molecular reaction shows a portion of the reaction mixture at 2 different times. So what is given here? So first A is decomposing into B plus C. So A here is green, B here is blue, and C here is yellow. Now, notice that each individual molecule splits into 2 molecules. So what is the molecular reaction showing here? So initially, how many were here? So 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 A's. At the end of the reaction period, there were only 4 A's. Right now, so they're asking you to draw a similar molecular scene of the reaction at t equal to 60 seconds. So for us to know what has happened first, we have to determine, notice that 8A has become 4A. So which means that for 8A to become 4A, it means half its concentration. So the time taken is T half. So this is a half-life period. Now, for us to find out the half-life period, we already found out the half-life, that the time taken between these 2 molecular scenes is half-life period. But we do not yet know what is the half-life period actually. So for that, we have to determine the rate concentration. So to determine that rate concentration, so they've also asked us to find the rate concentration of the reaction. Finally, total pressure of the mixture is 5 atmosphere at 90 seconds. What is the partial pressure of the substance B? So let's take an example. First one, we have to draw a similar scene at 60 seconds. So this here, the problem is incomplete. So this is t equal to 0 seconds, and this is t equal to 30 seconds. So they're asking us to find t equal to 60 seconds. Now remember that there are 8 A molecules that are becoming 4 A molecules in 30 seconds. In another 30 seconds, 4 A molecules will become 2 A molecules. So what will happen here? 2 of them will be consumed. The rest, the 2 greens will be left. So this is the molecular scene where 2 greens are left. Now we have found that the T half is 30 seconds. So they're asking us to find the rate constant of the mixture. So we already know that the T half is 30 seconds. We know that T half can be written as ln2 by K, or which can also be written as 0.693 by K. So K becomes 0.693 by T half, which is 30 seconds. So that value will give you, so that value will be 0.0231 per second. So this is, notice that here, this is the first per second, 1 by second or second inverse. So this is the first order reaction. So the T half, the K will be second inverse. So we have found the K value, so which is 0.0231 second inverse. Next, what is given here is that they are asking us to find at 90 seconds. Now notice that this is the 60 seconds. At 90 seconds, there is only one molecule left. Now, originally there were 8 of them. So 8 will become 16 molecules. So which is going to be 8 B's and 8 C's. So there were, let's take third problem. So if the total pressure is 5 atmosphere at 90 seconds. So what is the scene at 90 seconds? At 90 seconds, we have 1 A molecule, we have 7 B molecules and 7 C molecules. Right? Notice that, remember that at 60 seconds, so at 30 seconds, there were 4 A's. At 60 seconds, there were 6 A's. At 60 seconds, there were 2 A's. And at 90 seconds, remember that half-life again, 1 A. So you only have 1 A left now. So which means that the rest, which is 7 A's, have been converted into 7 B's and 7 C's. So 7 B's and 7 C's. So they have given that the total pressure is 5 atmosphere. They are asking us to find what is the partial pressure at B. Partial pressure of B can be written as the mole fraction of B times the pressure, total pressure. So what is the mole fraction of B? The number of B molecules present, which is 7, by the total number of molecules present. So that is 1 plus 7 plus 7. So that will become 7 by 15 times the total pressure is 5. So 5 ones, 5 threes. So which is going to be 7 over 3. That value will become 2.33 atmosphere. So this is the partial pressure of the molecule B at 90 seconds. So remember that mole fraction is the total number of the particular molecule by the total number of moles. So the total number of molecules are total of 15 and there is only 7 B's. So 7 by 1 plus 7 plus 7. So this is how we can determine the partial pressure of B. So use the same principle now. Pause the video right here and try to solve this problem. So next, let's try to determine the half-life of a first order reaction. So what is given here? So cyclopropane is the molecule that they've given. So they've given that the rate constant is 9.2 per second. What is the half-life of the reaction? And second, how long does it take for the concentration of cyclopropane to become 1/4 of its initial value? So let's start with the first thing. We have to determine the half-life. Notice that they've given that it's a first order reaction. So first order reaction, the formula is ln2 by k. So which is going to be 0.693 by k. So 0.693 by, the k value is given as 9.2 per second. So the half-life value will be equal to 0.075 second inverse. Now they are also asking us to become 1/4 of its initial value, the total time. So for 1 to become 1/2, it is taking 0.075 seconds. Half, because remember that again, half of it, which is 1/4, takes another 0.075 seconds. So the total time to take 1 to 1/4 will be 2 times that of 0.075, so which is going to be 0.15 second. So for 1 to become quarter of its value, it will take 0.15 second. So this is how you can solve the problem. So use the same principle now. Pause the video right here and try to solve this problem. Next, let's talk about the half-life equations for other orders. So for first order, we also determined that the T half does not depend on the initial concentration, but it does depend for the second order reactions. So second order reactions, T half is inversely proportional to the initial concentration. So we can write it as 1 by k times a to the power 0. And second, for zero order reactions, so T half is directly proportional to the initial concentration. So the initial concentration by 2k. So this is the two formulas for second order and zero order reactions. So this is the overview of everything that we have discussed in zero, first and second order reactions with their half-life. So with that we end lecture 1. So in lecture 2 we'll continue the discussion on collision theory. I will see you again in the next lecture.